Okay. So, this block diagram is this is the way that actual drawing. Now, we will simplify for our analysis, we will simplify. So, how we will do it? This was drawn by hand, right. So, let me little bit enlarge it, right. So, ultimately what happened, that whatever I told you, that here the input you have to give an additional input, that contacted power. So, delta PL1 is CPF 11 delta PL1 plus CPF 12 delta PL2 plus CPF 13 delta PL3 plus CPF 14 delta PL4. So, that is here it is coming as GENCO 1, right. Similarly, delta P2, because all these things summed up and put it here, and similarly that is your for GENCO 3 it is delta PL3 and GENCO 4 it is delta P3 and delta P4, right. And then this area this one also, this is actual and this is your delta p ti 1. So, actual minus schedule is equal to delta p ti 1 to error. So, here also from that previous block diagram we have drawn this simplified version, right, such that it will be easy for realization. So, this is your delta p ti 1 to error. So, finally, this is AC 1 integral u 1 and I told you this is AC participation factor, this is also AC participation factor, right. So, this is actually, and this is power system 1 is that area 1 and area 2, and this is as usual actual tie line power flow, right. This already we have seen for conventional thing, right. So, if you look into that, here you have how many state variables. So, this is x 1, this is x 2, this is x 3, this is x 4, right, and this is your x 5, x 6, x 7, x 8, x 9, x 10, x 11. So, there are 11 state variables, right. So, A matrix will be 11 into 11, but another thing is that here one is that contacted load demand and reflected as a local load demand, that delta PL1 plus PL2 will be there. Here also delta PL2 local, actually delta PL1 local I told you is equal to delta PL1 plus delta PL2, and this one delta PL2 local is equal to delta PL3 plus delta PL4, right. And uncontacted power demand is there, delta PUC1 and PUC2. Because of that, that equation we have to write that in the form of x dot is equal to AX plus BU plus gamma into capital P plus another gamma into small p, right. We will see how it is, right. So, this way just hold on. So, this way we have to make that all state variable equations. So, if you do so just hold on. So, also note that I told you that delta PL local will be delta PL1 plus delta PL3 and this one will be delta PL3 plus delta PL4. So, in the proposed AGC implementation, contacted load is fed forward through the DPM matrix, that is disco participation matrix, to GENCO set points, that I told you. So, this is shown in figure 4b, I showed you just now figure 4b. So, delta PL, P1, P2, P3 and delta P4, this just I showed you the diagram figure 4b. The actual loads affect your system dynamics via the inputs delta PL local in general, that is delta PL1 local and delta PL2 local to the power system, right. That is power system block. Any mismatch between actual and contacted demands will result in a frequency deviation that will drive AGC to redispatch GENCOs according to AC participation factors, that is A-11, A-12, A-21, A-22, right. So, next is the AGC scheme, actually it does not require measurement of actual loads, right. So, the inputs delta PL1 local and delta PL2 local in block diagram of figure 4a and b are part of the power system model, but not part of AGC, right. Next is state space representation of the two area system in deregulated environment, right. The closed loop system, whatever it is, you write all the state variable equation, write your x1 dot, x2 dot, everything. If you write, it will be Ax plus Bu plus this gamma into capital P plus this gamma into small p. This is equation 10. So, here I am not writing all the equations x1 dot, x2 dot, it is understandable to you, right. So, A will be 11 into 11 matrix, B will be 11 into 2 matrix, because there are two control input U1 and U2, gamma is 11 into 4 because P is actually nothing but your your delta PL1, delta PL2, delta PL3 and delta PL4. That is why it is 11 into 4 matrix, and this gamma, this small p will be uncontracted power demand delta PUC1 and in area 2 delta PUC2. That is why it will be 11 into 2 matrix, right. So, details of this matrix are given below. So, just let me reduce this volume. So, this is my A matrix. So, this is completely 11 into 11 matrix. So, you please write is most of the elements are non-zero elements, right. So, this is your A matrix. If you write x1 dot, x2 dot all up to x11 dot. So, this is will be your A matrix, right. Similarly, your B will be this one, it is A dash 1 1, there upon Tg1 it is A dash 1 2. I have corrected all these things, right. So, this will be your B matrix, right, 11 into 2 BU. Then this is gamma matrix. This is because delta P1, P2, P3, P4 all are function of CPF, that contact participation factor, that you have to put. After that you will get this matrix. So, gamma, and this is capital P. So, your it is delta PL1, delta PL2, delta PL3, delta PL4. That is why this matrix is 11 into 4 matrix, right. For your, there should not be any confusion, right. U means, let me write here, U means U1, U1, U2. That is why this matrix is 11 into 2. Gamma means this one, that gamma P, capital P, that is nothing but your delta PL1, delta PL2, delta PL3 and delta PL4, right. That is why it is your 11 into 4 matrix, right. Gamma capital P, this is actually this part actually capital P, right. So, next is your as that other gamma, and this one, this gamma will be your what you call that 11 into 2. This is actually 11 into 2 because it is actually the small p is equal to delta P U C 1 and delta P U C 2. This is nothing but your P 1, the small one, that is the small P 1 is delta P U C 1 and delta P U C 2. So, this way you have to form that your what you call that your all the state variable equations x1 dot x2 dot like this, right. So, once you have got this one, right. So, all these things I have defined here, that u is equal to u1 u2, p is equal to delta PL1 capital P is equal to delta PL1 delta PL2 delta PL3 delta PL4, right, and small p is equal to your delta PUC1 delta PUC2, right. And integral control law, I told you u1 will be minus ki1 integral of AC1 dt and u2 will be minus ki2 integral of AC2 dt. ki1 and ki2 are the integral gain settings of area 1 and area 2 respectively, right. Now, we will study something. So, basically I will show you the dynamic responses also, but basically as far as classroom exercise is concerned, all things will be given in the steady state, right. So, no question of simulation in the classroom or this that, right. So, consider a case, this is the case 1, consider a case where the GENCOs in each area participate equally in AGC. That means that AC participation factor, that A11 dash is 0.5, A dash 11 0.5, A dash 12 is 1 minus A dash 11, that is also 0.5. Similarly, A dash 21 0.5 and A dash 22 1 minus A dash 21, that is also 0.5. So, AC that is your what you call that it that participate equally in AGC, right. So, that is why 0.5 0.5 0.5 0.5. Assuming that the load change occurs only in area 1, that means that in the your what you call in area 1, thus the load is demanded only by disco 1 and disco 2. So, if load change occurs only in area 1 means area 1 you have 2 distribution companies. So, load change occur only for distribution company 1 and distribution company 2, that is disco 1 and disco 2. Now, let the value of those load demand be 0.04 per unit megawatt each of them, that is delta PL1 is 0.04 and delta PL2 says 0.04, right, and delta PL3 and delta PL4 they are 0, right. And then suppose a your what you call a disco participation matrix, right, DPM is given like this, that is DPM is equal to 0.50, 0.50, 0.50, 0.4, rest all the CPFs are your what you call the 0, right. So, in that case what will happen, that basically this is my your disco participation matrix. Then what will be the contacted power demand? So, contacted power demand means, look, I am overwriting here for your understanding. So, this is my delta PL1, this is delta PL2, say this is delta PL3 and this is delta P3 and that is delta P4, right. So, this one actually is equal to this one into your power demanded by distribution company 1 delta PL1, delta PL2, delta PL3 and last one is delta PL4, right. So, this is actually nothing but your contacted power demand. So, this way you can write. So, this is given. So, that means your delta P1 will be 0.5 into delta PL1 plus 0.5 into delta PL2, that is all these two terms. Similarly, delta P2 will be 0.5 delta PL1 plus 0.5 delta PL2 and delta your P3 and P4 will be 0, because only load changes in distribution your what you call disco your distribution companies 1 and 2 in area 1, and this is the participation matrix is contact participation factor is given, and delta PL1 and delta PL2 is 0.04, right. Therefore, you can write directly from here that delta P1 is equal to 0.5 into your delta PL1 plus 0.5 into delta PL2, right. But we have taken that delta PL1 is equal to delta PL2 is equal to 0.04 per unit megawatt. So, basically it is actually as delta PL1 is equal to delta PL2. So, basically it will be 0.04 into 0.5 plus 0.5. So, basically it is 0.04 per unit megawatt, that is your what you call that contact power, that is delta P1. Similarly, it is also 0.5 for delta P2. So, delta P2 also will be equal to 0.04 per unit megawatt, right. Delta P3 and delta P4 will be 0, right. So, that means that at steady state, as this is the contacted power demand, that is your what you call this contact power, your contacted power demand, right. So, as this is 0.04, this is also 0.0, that means at steady state generating unit 1 delta Pg1 steady state, at steady state it will generate delta P1, that is the contacted power demand total, right, and that has to be equal to 0.04. Similarly, at steady state delta Pg2 SS, right, is equal to delta P2 is equal to 0.04 per unit megawatt. This has to generate at steady state, right. Therefore, that just let me move little bit up. Note that DISCO 3 and DISCO 4 do not demand power from any GENCOs, I told you already, and hence the corresponding contract participation factor columns 3 and 4 are 0. This is already shown, right. So, DISCO 1 and DISCO 2 demand identically from their local GENCOs, that is GENCO 1 and GENCO 2, and therefore, CPF 11, CPF 12 I told you 0.5 and this one also 0.5 each, right. And so, and how to compute contact power demand, that is shown, right. So, figure 5 actually shows the result of this load change, right. I will show you the figure. So, area frequency deviation, if you look into this, let me come back to the figure, right. Let me come back to the figure, that is figure 5. So, this is figure 5. So, this is actually dynamic simulation, that is you can, this is actually not through MATLAB Simulink, actually the code was written, actual code was written. This is not through MATLAB Simulink, but it was your what you call that code was run in MATLAB environment, but code was written, right. That is it is not Simulink, and after that when data were generated, it was plotted in the MATLAB, right. So, if you look into this, this is delta F1, this is delta F1, it is written in delta F1 in hard. So, at steady state the error is 0, this is understandable. Similarly, this is delta F2, So, at steady state that frequency deviation is 0, but only that during your transient behavior that oscillations are there. Similarly, this is your delta P tie 1 to actual. Actually, what happened that actual here actually for this case that your distribution companies area 1, its actually demand power from the GENCOs of that same area, right. So, there is no question of that actual, there is no question of your actual tie line power flow. So, scheduled tie line power flow will be 0, right. So, that is why that actual and error, this will give identical response. So, this is a steady state, it is 0, because you have that disco participation matrix, this is a disco participation matrix, only this block 0.5, 0.5, 0.5, 0.5, right. So, here all elements are 0, all are 0, 0, right. So, basically delta p tie 1 to scheduled tie line for that will flow whatever it here I told you multiple that all CPF 13 delta PL 3 CPF 14 delta PL 4 plus CPF 23 delta PL 3 plus CPF 24 delta PL 4 minus this one. So, here 0 0. So, no question of your scheduled tie power flow. So, basically for this case you can evaluate easily that delta p tie 1 to schedule actually is equal to 0, right, and error is equal to actual minus schedule. So, as delta p tie 1 to schedule is equal to 0. So, that means delta p tie error will be equal to delta p tie 1 to actual. So, that is why error and actual both will give the identical plot, but at steady state this is actually 0, because this is my 0 line, right. So, that means at steady state frequency deviation in area 1, area 2 and tie power deviation, this is actually 0, right. This is simulation, but I will suggest do the for this the way we have made steady state analysis for conventional your what you call that AGC, there we have given the expression of delta f SS delta p tie 1 to SS steady state error. So, here also for deregulated part is a small exercise for you, you derive it, right, you derive it. So, and you will find it is 0. So, next one is that your this is your delta p tie error for the same case, right, it is also will be identical plot actual and error. So, it is 0. Now, as delta p g 1 I told it will settle to 0.04. So, it is settling to 0.04, right. So, because at steady state that delta p g 1 steady state it has to be is equal to delta p 1 is equal to delta p c 1 and that was 0.04 that we have seen. So, that is why this is actually 0.04, right. So, it is matching. Similarly, for delta p g 2 steady state this also has to be 0.4 because delta p g 2 at steady state is equal to delta p L 2 is equal to 0.04. So, it is matching, right. But delta p g 3 and p g it has no disco has contacted with them because other elements of CPFs are 0 except CPF 11, CPF 12, CPF 21 and CPF 22. That is why the generation actually settling to 0, but during transient some oscillations are there, finally at steady state it is 0, delta p g 3 is 0, right. So, similarly, delta p g 4 if you look into that delta p g 4 at steady state it is actually 0, but during transient some oscillations will be there, right, but after that actually it is 0, right. So, this is the dynamic responses for case 1. So, that is all these things I have explained. So, this is figure 5 A, B, C, D, E, F, G, H I showed. So, some statement has been written that figure 5 shows the result of this load change, right, that I showed you everything I explained, right. So, area frequency deviation actual power flow on the tie line in a direction from area 1 to area 2 and the generated powers of various GENCOs following a step change in the load demands of DISCO 1 and DISCO 2, right. The frequency deviation in each area goes to 0 in the steady state, that also I showed you, but you do it you do the steady state analysis, take the you will consider for your EG analysis you will consider figure 4b and from there mathematically you find out what will be the steady state thing, but you know steady state that delta f 1 SS will be delta f 2 SS is equal to delta f SS, based on that you try to find out, right. And then your the frequency deviation in each area goes to 0 in the steady state, since there are no contacts of power between a GENCO in one area and a DISCO in another area, the scheduled steady state power flow over the tie line is 0, that I also told you, right. So in the steady state of generation of a GENCO must match the demand of the DISCO in contact with it. Expanding equation 8, we have this expression in general, delta peta is equal to Cpf I1 delta PL1 plus Cpf I2 delta PL2, right. That is from equation 8, right. That is from equation 8, whatever sigma we have written, the sigma of this thing, Cpf your Ij delta PLj. So then Cpf plus Cpf I3 delta PL3 plus Cpf I4, this is equation 13, right. Now delta Pg1 steady state, I told you it will be equal to contacted demand, this is 0.04 per unit megawatt. This has been explained, everything I have explained before, right. Similarly, the delta Pg2 steady state also I told you that it has to be 0.04 per unit megawatt, but delta Pg3 steady state is equal to delta P3 will be 0 and delta Pg2 steady state is equal to delta P4 will be 0, because delta P3 and delta P4 will be 0. All these things simulation thing also I have shown, but your objective will be steady state only, right. But for the sake of completeness, dynamic simulations are shown, right, responses are shown. Now figure 5 also shows the actual generated powers of the GENCOs, right, reach the desired values in the steady state. Figure 5 already I have showed you, right. When you will read this one, you keep figure 5 separately, right, you download and just see this, right. So GENCO 3 and GENCO 4 are not contacted by any DISCO for a transaction of power, hence their change in generated power is 0 in the steady state, that is delta Pg3 steady state is 0.0 per unit megawatt and delta Pg4 will be 0.0 per unit megawatt, right. Now next is your case 2. In this case what happened, that we have considered another case, that here we will consider that all the DISCOs have contact with the GENCOs for power as per the following DISCO participation matrix. This DISCO participation matrix DPM we have considered, right. So if you, but you have to consider in such a fashion that if you sum up all the column elements, it will be 1. So it is 0.5, 0.2, 0.3, so it is 1. If you add, it is 0.25 each, so it is 1. So this one also, that all are 0 except 1, so summation is 1, and here also all column element you add, it will be 1, right. So that is your DISCO participation matrix. Suppose this DISCO participation matrix we have been taken. So it has been taken. So in this case, you have to find out the delta Peta you want to schedule, at the same time delta P1, delta P2, delta P3 and delta P4, that is the contacted power demand. And at steady state, again I am telling that at steady state, for this case delta Pg1 SS has to be is equal to delta P1, right. Delta Pg2 SS is equal to delta P2, right. Delta Pg3 SS it has to be is equal to delta P3. So delta Pg4 steady state is equal to delta P4, right. At steady state this has to happen. So in this case it is also assumed that each DISCO, just hold on, in this case it is also assumed that each DISCO demand 0.04 per unit megawatt. That means that each DISCO, that delta PL1 is equal to 0.04 per unit megawatt, right. Delta PL1 PL2 is equal to 0.04 per unit, I am overwriting it, but it is readable to you, right. Then delta PL3 is equal to 0.04 per unit megawatt and delta PL4, right, is equal to 0.04 per unit megawatt. For it is not necessarily mean all will be same, it may be different, all will not necessarily mean that it will be same, right. So and second thing is that what we are choosing, that we are your what you call your in define, and this AC participation factor, that APF, that A-11 we have taken 0.75 and A-12 0.25. That means in area 1 this is the AC participation factor, and in area 2 A-21 is equal to A-22 is equal to 0. That means that that means no control input is going to the your what you call GENCO 3 and GENCO 4, because AC participation factor actually it is no, not 0, we have, in this case we have taken, sorry, 0.5 we have taken, right. So, as A11 dash 0.75, so at the area, at that area 1, that input signal is U1. So, for GENCO 1, that is the generating unit 1, GENCO 1, that input actually going to 0.75, right, because this A11, just hold on. So, that in the your what you call for area 1, that output of the control is U1, right. So, GENCO 1, that GENCO 1, right, that your input is going to that GENCO 1 will be actually this A in general A dash 11 into U1, that is your 0.75, your what you call, that is your that is it is U1, right, is equal to 0.75 U1, right. This is your GENCO 1. Similarly, for GENCO 2, the input actually your U1 into your A dash 12. So, it is nothing but 0.25 U1, right. This much will go. Similarly, that in the case of area 2, A dash 21 is equal to A dash 22 is equal to 0.5. That means, the input to GENCO 3 actually it is going to 0.5 U2, and for GENCO 4 it is also going to 0.5 U2, right. This is the idea, this is the idea. So, now note that AC participation factor, again I am telling, it affects only the transient behavior of the system and not the steady state behavior when uncontacted loads are absent. If uncontacted loads are not there, then that AC participation factor actually it your affects the transient behavior, but not the steady state behavior. So, the scheduled power flow on the tie line in the direction from area 1 to area 2 is given, that is in equation 4. So, this equation 4 we know this equation, right, this already given. Now, if you expand this one, so it will be in this form. Now, the disco participation matrix, it is here, this is CPF 11, CPF 12, CPF 13, CPF 14 and so on. So, you know all the elements of this matrix. So, what you do, you substitute all these values of CPF and delta PL1, delta PL2, delta PL3 and delta PL4, they are all same 0.04 per unit megawatt, and substitute all these CPF values here, everything has been substituted, and then you will get delta P tie 1 to schedule actually minus 0.02 per unit megawatt. This is your what you call that delta P tie schedule power you calculate. So, we know that delta P tie 1 to error, right, 1 to error is equal to delta P tie 1 to actual minus delta P tie 1 to, that is your schedule, right. But a steady state delta P tie error it has to be 0. If it is 0, then delta P tie 1 to actual, right, is equal to, it has to be delta P tie 1 to schedule, right. So, but delta P tie 1 to schedule will be minus your 0.02 per unit megawatt, that means at steady state delta P tie 1 to actual must be is equal to minus 0.02 per unit megawatt, right. This we will see, I will show you the dynamic responses also, right, but this is the philosophy that how you can do this. Thank you very much, we will back again.